All right, let's look at notes 1-8. Infinite limits and behavior. Okay, what we're going to be exploring today, different than in the past, is in our limit problem, we're going to look at as x approaches either the positive or negative infinity. And if x takes on larger and larger values or smaller values, we're really discussing the end behavior of the graph. What the graph looks like as it comes on the screen and what it looks like when it leaves the screen, so to speak. So what we've been studying so far is mainly as x approaches some particular c value. So that's going to change. In a previous video, I looked at this just lightly, a little bit. Now we're going to explore it a little bit more in detail. All right, we've got polynomial functions to start us. Okay, we recognize this is a cubic. Okay, if you're asked to find the limit of this function as x goes to infinity or x goes to negative infinity, they're really saying to you, using notation, to consider what's happening to the ends of the graph as it leaves the screen and what it looks like when it comes on the screen of your calculator. So you could either pick up a calculator, graph this, observe the behavior, answer these questions, or if you've got skills, think about a cubic with a negative coefficient. It would have this general shape, this basic shape. And from this graph now, we can answer these limit questions, okay? As x goes to infinity, the further out I go, the y values get smaller, so I know my answer is negative infinity. The limit as x goes to negative infinity, the y's are going to get increasingly larger, so we say that limit is positive infinity. Let me stop here and make sure you're clear about this point. My answers are infinities because I'm describing end behavior. In no way do we need to put does not exist on these answers because I'm not approaching a particular c value, okay, where I have a vertical asymptote. It's a different context. Okay, I'm talking about the ends of the graph, and they can certainly very well approach larger numbers or smaller numbers. Okay, let's look at this other polynomial function right here. Okay, with a calculator or without one, fourth degree function, negative coefficient, general shape. Limit questions based on this graph, our knowledge of this graph. Okay, as x takes on larger values, our y's go to negative infinity. As you go to negative infinity, our y's take on smaller values too. Again, I would not say does not exist in either of these cases because it's a valid description of what's happening at the ends of the graph. We're not encountering any vertical asymptotes. All right, we needed this to help us with this next part of this lesson. We needed these polynomial functions to help us with rational functions. Okay, and hey guys, rational functions, ratio, fractions, okay, a rational function is just made up of a polynomial in the numerator and a polynomial in the denominator. That's all. Okay, I want you to kind of see this on the screen and know that there's more information down here below that we're going to be referencing. Okay, all right, so for this first example right here, you're asked to find the limit as x goes to infinity and negative infinity of this function. Well, you can either, one, pick up a graphing calculator, look to see what the graph's doing at its ends, okay, or if you remember from a previous course, pre-cal, okay, if you remember what that parent function looks like, you can quickly sketch the new graph without a calculator. So real quickly doing that, if I move the parent function left 5, so the graph is shifted left 5. Graph looks like this. Comes together at the asymptote. So graphically producing it by hand, we can see that as x takes on larger values, that the y's are getting closer and closer to the positive x-axis, getting closer to 0. From above the x-axis, but still coming in closer to the x-axis. Likewise, going out to negative infinity, we get the same limit. Okay, so graphically, you got a calculator, great. Don't have a calculator, you see what it looks like, produce it, get the limit answers. Now, that's not going to be so easy over here because we have no idea what that graph looks like. Okay, so this is one strategy. All right, some other strategies also to consider is this. You might want to numerically, if it's manageable, not so much over here, but definitely better over here. If it's manageable, think of very large numbers to put in for x, like a billion. Add 5, square it. Well, you're going to get this super large number, super large. 1 divided by super large is 0. So, I mean, you can almost reason through this one numerically and come up with these answers. And it would work the same for negative infinity plus 5, you know, a negative bazillion plus 5 squared. 1 divided by that large number, of course, is 0. So, you know, graphically, with or without a calculator, manageable here. Numerically, manageable here. Not so much over here. So let's look at some other options. Okay, something else that we can think about is from our past classes, Algebra 2 and Pre-Cal, where we compared exponents in the numerator and denominator. So let's just kind of take a peek in down here at the bottom of the notes. Okay, and just some descriptions here too of vertical asymptotes and holes, removable discontinuities, also point discontinuities. Okay, but really down here is where I want to focus. Okay, asymptotic behavior of rational functions. Okay, and behavior, asymptotic behavior of rational functions at its ends. So we have this function, it's f whatever. We have a polynomial on top and a polynomial in the denominator. We call this p, we call this the h polynomial. It creates a rational function. In previous math classes, you learned that if the degree, that's what this notation is, the degree of the numerator, what's degree? Well, that means the highest exponent in the numerator, is less than the highest exponent of the denominator, degree of h, then the limit as x approaches either the positive or negative infinity is 0. You learned in Algebra 2 that this rule implies that we have an end behavior asymptote that's horizontal. This is a horizontal asymptote. Y equals 0. When you compare the exponents. There's 3 cases or 3 comparisons we can make with degrees of the numerator and denominator. You saw that. Well, in calculus now we can talk about describe end behavior using limit notation. So this is really Algebra 2 over here, and this is really calculus here. So the limit of the function as x either goes to positive or negative infinity goes 0. And in our first example up here, that's what happened. Okay, the other case that you learned previous is that what if the exponents are the same in the numerator and denominator? That is the highest exponents. Well, you learned, all right, you compare the ratio, okay, of the coefficients of the lead terms. And so now you still had a horizontal asymptote, but it didn't occur at the x-axis. It occurred at some other k value, a shift up or down of the x-axis. The graph leveled off at some other asymptote, horizontally speaking, besides y equals 0. And then perhaps in Algebra 2, you learned that when the degree of the numerator, the highest exponent at top, is larger than the highest exponent in the denominator. I think you talked about something about squishing it, the graph, but you learned later in Pre-Cal that that produced a slant asymptote. Okay, and I believe last year in Pre-Cal, you did polynomial long division to find out what that slant asymptote was. Okay, but returning back up here to the second case, we have a horizontal asymptote. Okay, well, that's the Algebra 2 piece. If you look over here, this is the calculus piece. If this is the situation, then the limit is going to be a number, a ratio of the coefficients, k, just not 0. But it's still a horizontal asymptote. In this third case, when the degree of the denominator is larger, if we wanted to do polynomial long division, fine. That's going to be too much work for us. We're going to take a shortcut approach. That's the Algebra 2 way. Here, if we want to describe the end behavior, we're going to use this notation. Well, if the end behavior asymptote is not horizontal, okay, as in these 2 cases, okay, then we really, you know, right here, if it's not, we call it a slant asymptote, an oblique asymptote. We can't refer to it as a HA, horizontal asymptote. We just call it the end behavior asymptote. Well, that means if it's a slant asymptote, if x goes to infinity, the y values might be going to positive or negative infinity. That's what my answer looks like. Okay, it's not going to be 0 or some number k. Okay, my answer for this situation is either going to be a positive or a negative infinity. So let's see if we can kind of make some sense of all these rules again and refresh our memory about it back up here. Okay? All right. So going back to what we know is true, this example, we know the limit's 0. Okay, using what we know down here at the bottom, Okay, if I captured what I call the end behavior model, well, let me look at what that means. Let me first expand here. FOIL, box, whatever you learned. Okay. For what we're going to do, I think to manage this, to make this easy, okay, when we want to find these answer of zeros and we don't want to look at a graph and we don't want to use the numerical approach, okay, what I think I want you guys to look at is this. Consider capturing the end behavior model. Okay, the model meaning, okay, what has the most impact on the value of this answer? And that would be in the numerator, the term with the highest exponent, and in the denominator, the term with the highest exponent. So that would be 2. It's bigger than 1 here. And know that this is 1 times x to the 0. Okay. Certainly, you know, we want to look at capturing that. So let's consider now, right here, let me kind of do this. Okay. Looking at the end behavior model. Okay, so let's say that I wanted to consider looking at the limit as x approaches infinity of not this exact function here, but its model function. And all that means is that this is a good prediction of what this graph's going to do. Whatever this graph looks like at its ends, this graph will look like at its ends. And think about that. This, the parent function, is going to look just like this, okay, except this graph shifted over. So it's a good model for this behavior. All right, so we captured the end behavior model. We put the limit before it. Okay, now, okay, you can think about going down here and comparing your exponents if you want on this model, or even before you found the model, you could have compared the exponents. Okay, it's case 1. Look down here. The degree of the numerator is 0. The degree of the denominator is 2. Okay, my answer is going to be 0. I got that for both of these limits. Okay, so that fits. Everything's working. Okay, now the way I'm going to do it is this. It's the same thing. We end up with the same results. I captured the model. Now I'm going to substitute infinity in. I capture the model, do any simplifying I can. Now, evaluate this at infinity. What's 1 over infinity squared? Well, I think we talked about that numerically. This is super large, super, super large. 1 divided by super large is super small. That super small is 0. Okay, I can do the same thing here. The limit as x approaches negative infinity of the model, 1 over x squared, okay, equals 1 over negative infinity squared. So 1 divided by super large, again, is 0. So this is going to work in every case for us. So instead of having to memorize these different comparisons down here, like we saw in previous classes, we can now use limits to help us understand and get our mind around that. Okay. All right. So come back page. All right. So let's look at example number 2. Okay. So I want to answer these limit questions. Okay, for this rational function. In years past, we would have had you compare 3 and 3. Oh, they're the same. The ratio of the coefficients is negative 3/5. That's our horizontal asymptote. Fine and good. Let's just make sure our technique works. Okay, this way again. All right, what I'm going to do is I'm going to say the limit as x approaches infinity for this problem from k of x. And I'm going to capture the model. 3x cubed over negative 5x cubed. That's a 3. Okay, before you evaluate this in infinity, let's go ahead and take the time to simplify. Okay, well, x cubed and x cubed will cancel. That leaves me 3, negative 3/5. I'll just pull the negative up top with the 3. Doesn't matter where it goes. Well, there's no place for me to plug in infinity, so guess what? That's a basic limit. My answer is negative 3/5. So if you looked at this graph as it comes on the screen, okay, and it leaves the screen, you're going to see, okay, that it levels off at negative 3/5. Kind of hard to tell unless you really zoom in, but it would occur like that. Okay? Okay, you, like I said, confirm with the different cases at the bottom, and you'll see that that follows the case. Okay, let's look at number 3. Because looking at the time, I'm going to have to get through these here so that we're all good with getting it into Sophia. Okay? Okay. All right, let's look at 3. All right, so we've got this limit question. It's a rational function. All right, I could do the foiling here. I could see that 4 would be greater than the highest exponent of 3 once I FOIL. 4 being greater than 3, coming down here, case 3. My answer is either going to be positive or negative infinity. Which one? I don't know. All right. Let me say this is approximately, to get this answer, the same. It's actually going to be the same, but the answer is. Okay, I'm going to capture the model. So that would be the 3x to the 4th on top. Okay, if I were to do the necessary algebra, I'm going to get an x cubed down here. Can I simplify? Absolutely, I can. So the limit as x goes to infinity of 3x. So think about 3x and what it looks like. We know it's a linear function. So the behavior of this really complicated function is going to follow the behavior at its ends, just the ends, okay, of this graph. Plug in infinity, 3 times infinity results in infinity. So that's going to be your answer for this problem, okay? So let me stop it here, and I might have to finish this in another video.